then now we just do, we all know these are all zeros, so I'm just going to skip 2. So this is the zeros place, 1 place, 2, 3, 7. So I'm just going to skip these ones and just go here, so I know it's going to be 1 times 2 to the second power, and then the rest are all, hopefully, 0, 0, 2 to the 4 is 4. So since we know this is a negative number, I put the negative sign from, what was it before? So we got it as, this is negative 4. Okay. Which is good because I was going to go over this again. So, so how we convert binary to decimal is, like I said, we take the position. Always make your number, if it's a negative number, convert it to a positive number. Just remember that you got to put that sign over there, and then do 2's complement to make it a positive in binary, and then do the weighted position math. Yeah.
How did you get the negative?
Basically, because we said I had a 4-bit unsigned, 4-bit signed value, and so I knew because it's -1 out front here that my number was negative. So then I just said, okay, my number is going to be negative in decimal. So I just put that number. And so I convert over from my negative binary to a positive binary number. So it's not by doing 2's complement. So that way I get the positive decimal value of that number. And so that way I can just put the negative in front of that, because then I can say, oh, it's -4.
You have to do that conversion before you can convert to
Yeah, there's some, people have tricks, but I do it this way because it's a lot more, it's simpler, easier. So
Is that top number 74?
this one here?
Yeah.
Okay, so we do that one. So we are going to convert the top one. So 0, 1, 0, 0, 1, 0, 1, 0. So we got 0, 1, 3, 4, 5, 6, 7. So we're going to have 2 times 1 times 2 to the 6 plus. You can skip these when you show your work, because I understand what you're doing, because you know, hopefully you know those are always 0. I'm just going to go 1 times 2 to the third plus 1 times 2 to the first. So 1 times 2 to the 6 is
64.
64. Yep. 2 to the 3 is 8. And 2 to the 1 is 8, 72. Yep. So,
74.
oh, my bad. Sorry, I thought it said 62 there. Yeah, 64. Right. You have comments? Do you think we understand how to do binary and decimal? If you look online, they have some other ways. So I'm not saying this is maybe not the perfect way, but I do it this way because it works in all bases. Every base that I use, or use, or can use, this formula works for all of them. To go back to our standard decimal. And so we'll see that after I get done with doing binary. So now I've got to do the a lot more, I would say, harder conversion. So now we have to go to decimal to binary. We can do really big, like you can draw the table and keep adding 1 and keep going down, or we can do this formula here. Like I said before, there's another way to do other ways to do this. I do it this way because it's a universal way. So if I take, I'm just going to go with number 14. So I have decimal 14. So what we do is, I'll take 2. So this is, I'm sorry, put that backwards. We're going decimal. So we take binary as base 2, so we want to say this is the base, and then we're going to put the number here. So we put 14 here. So 2 divided into 14, 7. So then I'm going to need to, there you go. Need that. I'm going to go here and do it. We go into 7, so then we get a remainder of 0. I do it this way. So when we do this 0, this becomes our first digit in the binary. So the remainder is, right? So then now I go 2, then I take this number here and put 7 here. 2 goes into 7 3 times. So we get 3 times 2 is 6. So we get a remainder of 1. So then I put the 1 next to it. So now I take 3. 2 divided by 3. 2 goes into 3 one time. Remainder is 1. So I put that one up here. And then we do it again. 2 divided by 1. Doesn't work, so we get a 0. We get a remainder of 1. But 1 there. And because this is a positive 14, we're going to put a leading 0 here. Right. So we can verify it by going 2 times. One times 2 to the third.
I have a question.
Yes.
Why not just go by, I guess, 1, 2, 4, 8, 16, 32, 64, 128?
You mean I go in here and go,
Why not just do a simple addition, I guess?
Well, because if it's a huge number.
Well, a huge
Yeah.
number, it still stops, so like, I mean.
Like I said,
256,
there's
right?
multiple ways of doing it. Alright, that's what I said to me. I don't mind which way you do it. I guess I don't like, oh, you did it my way. You didn't do it my way. I'm gonna tell you. No, I do it this way just because, like I said, if I go, let's say I do hex, decimal to hex. What if I do base 7 to those kind of things? And so basically is I can do the same. I just know one formula, and it works for every base that I have. So that's why I go with it. Yeah. But your way works as well. So no problem.
So, I don't understand why you got the 0, 2.
Which one? Oh, this is like I did before. Just like
Base 2.
it just tells me it's base 2. If
Oh,
I
that's
go,
base 2. Oh.
It's probably better to go B. Let's have to clarify it.
So that's the answer, 0, 1, 1,
Yeah.
0.
0, 1, 0.
And you
Like I
just
said-
use the remainder as the,
Yeah, you use the remainder. So basically, if you don't actually write out this, you just say it's you want to go from least significant bit to most significant bit, or most significant bit up to least significant bit on the number.
so which direction is it going? You're putting
0 goes
here.
here. Sorry, and then 1, 1. So this is least significant. This is the most. This here is my sign bit. So that's what I did there. I just added this to make it tell me my sign. Because I left that off, you're like, I have to either say this is a 4-bit unsigned number, or say, or add 0 and say this is a 5-bit signed number. Right? Yeah.
Can you give us a difficult one
Yeah.
to test it?
Everyone's done? I don't need to erase this. probably the highest number I would give you, probably like a 300 number. So I'm just gonna give you, try 96. So take a few minutes and do 96. Who has it? Who wants to come up and do it? You already done one. That's no different. Who wants to do it? You want to do it? Okay, go ahead. And show you works that way we can.
So we divide by 2, we get, we'll get the remainder of 0. Divide by 2, we get 1, 0.
Nice. Very good. Alright. So hopefully you see what we did. It's the same way that I did the right half by hand. I accept this as showing work as well, because I can see that your remainder is 0. And you just divided by 2. So it's another way to show your work. So, any questions? Alright, you want to go another sample, or I think we're good on that one? So what if I did something like this? Alright, it's a really, really long number and really annoying to see, let alone write. And if you're trying to copy this down in your notes, you might mess up on zeros or ones, and so basically we need a better way to display this number, right? So that's why we use hexadecimal numbering system. That's X. This is base 16, right? So the digits that we have for hexadecimal, we go 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E. E and F. Right? You can have these capitalized lowercase. I'm not picky. I'm not going to dock you for them. And so the notation is like A5. You have like the 16 notation down below, like we did on the other ones. So this is the subscript to distinguish hex from the other numbers. We have A5, we can write hex.
Is that a comma?
Yeah, it's a comma. And the other way is what we do in C coding. It works in other C sharp. You write the X, OX, and 0X, A5. So that's another way of writing it. So this is how we distinguish. This is how humans would distinguish. We use this as well. And then computers, how we distinguish a regular decimal number in programming a decimal number. Right? So, what we're going to do,
How do I get the OX?
OX, 0x. It's just like in programming, in C, C sharp, if you want to distinguish, like if I go int x equals, let's say, 23, I'm not going to convert this, so I can also, it's not going to be the same number, I'm just going to put a number here. I can go 0x A5. Basically it says, oh, it's going to be hex A5. This is, decimal. This just tells the compiler basically that, oh, I'm using the hex number instead of a decimal number.
So the A5 is the real number, OX just the indicator.
Yeah, this would be the indicator.
Is that
Like
the-
before we did the binary, like I had 0B.
Is that the letter O or the number 0?
Yeah, the number is 0. Number is 0. It goes 0x.
You
0B.
don't put a little dash through it?
Oh, dash? Yeah, I can do that. Right. Yeah. I took some engineering classes, and so I get used to writing so that was better. That clarifies. So, right. That's why this basically just shows that you can use, that kind of notation in your programs as well. So then we create the hex table. So these are your binary numbers. So if you want to say this is decimal, these are binary numbers. And these are hex. Hex is one of the nice base systems because you're able to, basically is 4 binary numbers represent 1 hex number. So like I said, 000 is 0. 1 is 0001. 1.
What happened to 3?
Wouldn't hex be number, wouldn't hex be
3's there. Okay, yeah.
Oh,
I skipped ahead of myself. 3 here. Alright. I'm counting down this way as I'm going across. So.
Wow.
So make sure you clarify this is unsigned. So unsigned, unsigned. But it doesn't really matter. Let me see if it is. So I can go like this. 4, 4.
There's 5 in that one.
There's 5. Basically, now we just go along and go. Okay, 101, A, 10, 110, 6, 0, 1, 0, 5, 101, A, and A again. So this big long number is A, 5, 6, A. So we can take basically that what it is, we can represent a lot fewer bits.
But then can you add it, like, it says decimal number of 10 is equal to A. There's 3 A's, so that'd be 30 plus 5 plus 6. Would that give us? No.
Don't you have to do like the bases too? It's like the first characters of the 1 and then the next is 10 and 100 or something.
So you want to turn this to decimal?
Like no, if you just want to solve for the value of it.
Yeah.
Yeah, you want to convert this to decimal, basically.
I guess.
I don't want to do that big number.
I'm just saying,
So.
if you needed the value,
Yeah,
what would be the process of getting the value?
yeah, we'll do that in a second. So everyone clear on, basically this is how I basically, if you want to say, this is the conversion from binary to hex, or hex to binary. I build this table every time. It's the simplest way to convert hex to decimal.
So is the main purpose of hexadecimal getting from a big binary number to a decimal number?
Yeah, it's one of these. Because if we saw that on the screen, it would just be hideous. But we saw this on the screen, it's a lot more user-friendly. Basically, especially when you use 32-bit processors, it's easy to look at it in hexadecimal than big giant binary number. So, any questions? Okay, so we're going to answer yours. So now we're going to go from hex to decimal. There you go. What am I doing? Because I'm doing a pretty big number. Alright, so we're going to have 4A, 8E. So we did the same thing before. So hex was what base?
16.
16. So if I go 4 times 16, so this is the zeros place. 1, 2, 3. So it's 16 to the third plus A times 16 to the 2 place plus 8 times 16 to the 1's place plus E times 16 to the 0. Right? So let's say that's 10, right? And E was 14. So we do that way. So we use a decimal number, 10 in that place. We use E is decimal 14, so we place that in there. So then we can do the math. I want to say this is 16,384 plus 25,600 plus 28.
Wait, 25, 600, you must do 0 then, right?
Which one?
2,560 or is it 25,600?
Yeah, it's 2,500. You have a calculator? Let's go 10 times 16 to the 6th power.
You just said one thing and wrote
Oh.
Yeah, you
another.
said one thing and you wrote another.
Yeah, okay. What I wrote is correct.
That's a,
And then, of course, 0 to 16 is 1, 1 times 6 is 14, and then so we get 19,086 is the number. Okay. So we use the same convention to go, so basically binary to decimal, we do the same convention, text to decimal. Okay. Forgot to mention is if you go into Windows and you go to Calculator and you turn it to engineering or scientific, I think engineering, you can actually you can type in a decimal number and there's you click on a button that says hex and then it will convert it for you to hex. And so you can use that for help to make sure verify your answers are correct. Basically, to study, it's a good way to do it. It also has anding and oring, so you can test your anding and oring and adding binary numbers together using that tool. I didn't bring a calculator with me, but my TI calculator does it as well. So it's binary.
As you're going from left to right, calculating, is it safe to say that the numbers as they go right would have to be smaller so that you know you messed up on your math if that were 25,600? Wouldn't it have to be smaller than 16,000 since it's moving to the right?
Yes. Yeah. Hope I understand what you're saying. It's basically this number is smaller than this number.
Right, as
Yeah.
you go to the right,
Oh, these
in
got bigger.
decimal, the numbers would have to
Yeah, they get
increase.
smaller as they go down.
So that's a way you can make sure you're on the track.
So, I won't give any bigger. I would just give you maybe 3 numbers. I won't give you too big of numbers, just because when you start getting this big and you don't get calculators, you start messing up. But it's not too bad. I mean, you just do it longhand, 16 times 16 times 16. Hopefully you remember that from algebra. So that's how we go to hex to decimal. Okay? Next. So now we'll go to decimal to hex. Now, I don't mind which way you do this in homework assignments or in your tests or quizzes. If you want to go from decimal to binary, then binary to hex, I'm okay with that. Either way, it works. You converted the number from decimal to hex. Or I can do what I'm going to show here, and there's some other ways as well on the internet. But what I did before is, so we're working in base 16. So we're going to convert the number, let's do 127. So we'll do it the same way. So put my base there, and then my number is 127. So then 16 goes into 127. Sorry about that, there's the wrong number. I did 16. I did 2038. Sorry. So 16 goes into 2038. How many times? Sorry, it's 127 times. So then we get, well, I basically say 16 goes into 21 times. So then we get 16, 4. We carry that down. 16 goes into 438. It goes into 43. Twice. 2. 16 times 3, so we get 32. So we get 1, 1, 8. 16 goes into 118 7 times. We get 112. Gonna get 6. So So, that's how I do it longhand. Like I said, you're gonna do it longhand, so again, remember how to do your division. So we get a remainder of 6. So like we did before, this is our least significant bit digit. So put 16, 6. So then now we take 127 and divide that into it. So it can't go into 1, it can't go into 12, goes to 127, basically lead it here, 4 is 7, lead it 112, get a remainder of what, 15? But, so we get a remainder of 15, but since we're doing hex, 15 is F, so we would have put F on top. So then we use,
Does it matter if it's capitalized or not?
no, I don't mind. I try to reverse it on you, so I try to do different bases and different capital and lowercase. So, as long as I know, distinguish it that it's the letter F.
You put the 16 there to indicate that it was a base 16.
Yep.
Is that why that's?
You gotta keep track on me because I will dock you on your test and homework, so dock me on my not doing it as well. When I'm doing this kind of math, it's okay.
So every time we catch you, we get extra credits?
No.
Oh.
This makes me know that you are actually correct. So you take 7. So you know that 7 doesn't go into 16, so you get 0, 0, 7, so remainder 7, and 7 is the right digit, so we get 7F 6, 16. That's how we can go straight from decimal to hex, without going to binary first. And
Okay, that last 7 that goes up there, which is first in the hexadecimal number,
Mhm.
is that coming from
it's coming,
dividing, or the remainder?
yeah, it comes to the remainder. So basically, this is 0, and the remainder is 7, so the remainder comes up. Same way we did in binary. In binary, again, we had we did like 2 go into 1, we could go into 1, so then we had 1, which was remainder 1. Brought that 1, put it up in the binary number. The same way we do, we take the remainder and put it up.
So but that 7 is the number of times that 16 went into 127, right?
Well, but for, like, this 6 is here, this 15 is this F, and this 7 is that 7.
Wait, but how do we get that 7 though? Like, why are we dividing
Oh,
7 by
because,
7?
well, we have to still do, basically we take this number, we want to get to 0 in our end number on top, or I can say down here, because then if we do it again, 16 goes into 0. We're dividing
By 0.
by 0, so we're done. We want S to say, so we're done after that. We take this number, we said, this is our original number, we divided by 16, so we got this number, 127. And then we divided 16 into 127. We got this 7 here.
Yeah,
Put it
that's what I
down
was
here.
asking. Like, is that 7 because 16 went into 127 7 times?
Yes.
Yeah.
Yeah.
Sorry. Easy, all right? So hopefully you see, we did the exact same thing we did in binary. The only difference was, in binary we had the base with 2 here instead, and in base hex we did 16. Right? So then we can do what we call base n. So I can give you any base. I use big giant capital letter N. Basically, I can go base 3, base 4, 5, base 6, 7, 8, 9, 10, base 124. You keep doing that. So, in essence, you can think of, we had to create some kind of a digit format for us. Kind of like, your kind of formula you would go. So, n minus 1, well, n is greater than or 10, and then you can use, I'm just gonna read this, use letters for n greater than 8 or 10. So, then you run out of our alphabet.
So it
you
should
go
be
to
less than 10, right?
Yeah, shouldn't
Yes,
it be less
my
than
bad.
that?
No, the top one.
Yeah. Less than 10. My bad. Alright. So, instead of hex, we had 16, so we had 0 through 9, and then when we went to 10, we went to letters. And we put letters on there. Basically, is we just need to basically create symbols for our numbering system in base. This is kind of what I formally use in this class, so that we all kind of on the same page when we do different bases. Yeah.
Is there anything that we need to learn from the book for the quiz on Monday?
There's no quiz Monday. No quiz Monday.
Oh,
No class Monday. No quiz Wednesday. No quiz at all next week. No quiz.
Awesome.
I'll write on the board when there's a quiz. So.
We have to have chapter 3 next week, right?
Yeah, we'll start. There's a few more things we gotta do in chapter 2.
Okay.
So.
But do you want us to read ahead of chapter 3?
Yeah, finish chapter 2. Finish chapter 2. Don't read chapter 3 yet. Just finish chapter 2. But yeah, I think there's like only like 4 pages or 5 pages left. Read it. Let me do. So if I want to say n to decimal. So I'm just going to mark this as the next one. So these are just some imaginary variable names that could be placed with any numbers. And so if you want to say, so we're going base n to decimal. You want to say it's a1 times n to the third plus a2 times n to the second power plus a2.
Will we ever use other bases other than hex and binary?
Hex, you also use what is known as an octal,
Okay.
base 8. Some people like using base 3 sometimes. So basically we gotta do all bases. So
What's the advantage of base 3?
um,
Less digits than binary.
yeah, basically. If you look at Google up there's a computer based on base 3. So basically it's like true, false, and somewhat true or something like that. So it's a theoretical computer that they build for science research and stuff. Basically this allows us to represent more digits and voltages. Basically now we can measure voltages. Either it's not on or off, it's either on, somewhat on, and off.
It's on, it's thinking about it.
Well, it sounds like they're trying to make it more like an analog computer.
Yeah, that's probably a better way to say it. We'll continue this on